Have you ever wondered which questions do usually come in system design interviews at Facebook? This video is the second part of the two-part video series on system design interviews at Facebook. To recap, we discussed the following in part 1 of this series. 1. What are the system design interviews at Facebook? 2. Design Facebook news feed. 3. Design Facebook status search. 4. Design live commenting at Facebook. 5. Design Facebook Messenger or WhatsApp. And 6. Design Instagram. In case you haven't watched the first part, you can watch it by clicking the above link in the top right corner of this video, or through the link that we have added in the description box below. Also, subscribe to our channel, and press the bell icon to get notified for our future videos. For now, let us review the next 5 top system design questions, which are usually asked at Facebook. Design proximity server is a popular system design interview question. On Facebook, the proximity servers are used to discover nearby attractions, such as places and events, which are then recommended to the users. In this question, we will be asked to develop the backend of such a system with the following key features. Users can add, update, and delete places. Given a location expressed as latitude and longitude, users can query all the nearby places within a given distance. One optional follow-up to this question is to also query events happening near a given place around a particular time. This basically adds the third dimension of time to the problem. While designing this system, we should ensure that the system has minimum latency. So, the user does not experience any significant lag during the queries. The final design should be highly available. As we know from the CAP theorem, that we can have either high availability or high consistency, thus, we will aim for an eventually consistent system. Also, our system will be read-heavy in nature as more users will be searching for places rather than adding places. Thus, the number of read requests will be far greater than write requests. To design an efficient system in the interview, we will have to consider the following scale estimations. These estimations will help us in explaining the scale of the system to the interviewer. On average, the system will have 1 billion daily active users and receive around 5 billion search requests daily. Also, about 500 million places will exist in our system. Now, let us discuss the REST APIs we will develop for this problem. To interact with the system, we will need 2 REST APIs. The first one is the Search Nearby Places API. It is a read API to fetch the nearby places for each user query around a given location. The client will send user ID, search query, user location, maximum results to return, page number, and timestamp as the request parameters. The second one is the Add Place API. It is a write API to add a new place and store it in our database. This API requires user ID, place name, place location, and timestamp as the parameters. Next, we will discuss the high-level design for this problem. At a high level, we will need to store and index all the places. To query this massive database, the indexing should be read efficient, as while searching for nearby places, users expect to see the results in real time. Thus, let us explore the different storage solutions for this problem. One easy solution could be to store all the data in a database like MySQL. To find all the nearby places of a given location within a given distance, we can do the following query. Select star from places where latitude is between x minus d and x plus d, and longitude is between y minus d and y plus d, where x and y are the coordinates of the location, and d is the distance. However, this will be inefficient, as the query will need to perform the intersection of 2 massive lists of places, one along the latitudes, and the other along the longitudes. We will need to shorten these lists to improve the performance of our queries. A better way is to divide the entire world into smaller grids. Each grid will store all the places within a specific range of longitude and latitude. Given the user location, we will find all the neighboring grids and then aggregate them to return all the nearby places to the user. So far, we have only considered fixed-size grids. There is a potential problem with them. Some grids will have a large number of places as compared to others. For example, the grid containing New York City will have a far greater number of places than the Great Sahara Desert grid. Thus, we will need to improve our design by using dynamic size grids. To implement dynamic size grids, we will use a data structure called quad tree to represent them. A quad tree is a tree where each node has 4 children. In this approach, we will denote each grid as a node in the quad tree. If a particular grid has more places than a specific threshold, we will divide that grid into 4 more grids, meaning that the node will have 4 children containing places from each quadrant, as shown in the image. Some of the crucial questions that need to be answered in this question are as follows. 1. How is the quad tree index built for quick retrieval of the relevant places? 2. How to store and shard the quad tree index, distributed across multiple servers? 3. What happens if an index server dies? How to rebuild the index and create a fault-tolerant design? 4. How do we find the neighboring grids in the quad tree index? And 5. What happens if an application server dies? And how to balance the load across multiple application servers? Now let us review the architecture diagram of this system. This is the detailed component design of this system. It involves various components like the quad tree index, databases for storing places, caches for fast retrieval, application servers, load balancers, and the search ranking service. This question can be quite complex and deserves its own video. Do not worry about it. We will make a separate future video to discuss this design in more detail. So, subscribe to our channel to get notified. For now, let us move to the next frequent question. On Google, you may have noticed that as you type your query in the search box, it predicts and suggests a list of autocomplete queries, based on the characters that you have already typed. These suggestions are called Typeahead suggestions, and they help enhance the user experience, and better articulate their search queries. Thus, in this question, we will be asked to develop a service that suggests the top 10 search queries, based on the characters already typed by the user in the search box. For simplicity, let us assume that the query's popularity can be determined by the frequency of the query being searched in the past. Next, let us discuss the design goals and scale estimations for this question. While designing this system, we should ensure that the final system has minimum latency, and users should not experience any significant lag while typing their queries in the search box. The design should be highly available. And thus, due to the CAP theorem, we will aim for an eventually consistent system. Also, our system will be read-heavy in nature, as for every search query, multiple read requests will be issued to get the Typeahead suggestions, as the user types the search query. However, only one write request will happen at the end, to save the final search query in our system. For an efficient system, we will have to consider the following scale estimations. On average, the system will have 1 billion daily active users, and receive around 10 billion search requests daily. Each search query will be about 25 characters long. Thus, around 250 billion daily read requests will be made to our service, to get the Typeahead suggestions. Now, let us discuss the REST APIs that we will be developing for this problem. To interact with the system, we will need 2 APIs. The first one is the Get Typeahead Suggestions API. It is a read API to fetch the Typeahead suggestions for each ongoing search query. The client will send user ID, search query so far, maximum results to return, and timestamp as the request parameters. The second one is the Add Query API. It is a write API to add the final search query to our system. This API requires user ID, search query, and timestamp as the request parameters. Now, let us discuss a high-level design for this problem. As we may have noticed, this question is very similar to prefix search. The data structure which can efficiently perform prefix search is called trie. It is a tree-like data structure that stores phrases, where each node stores a character of the phrase in a sequential manner. To get the top 10 Typeahead suggestions efficiently, we can store these suggestions with their count at each node of the trie. This will require extra storage, but will improve the performance of our read requests significantly. We can optimize our storage by storing only references to the terminal nodes, rather than storing the entire phrase. To find the suggested terms, we need to traverse back using the parent reference from the terminal node. We will also need to store the frequency with each reference, to keep track of the top suggestions. Some of the essential questions that need to be answered in this question are as follows. 1. How will we build and update the try with the new search queries? 2. How will we store and shard the try across multiple servers? 3. If a try server dies, how will we rebuild it to achieve a fault-tolerant design? 4. What happens if an application server dies? And 5. How to balance the load across multiple application servers? Next, let us review the detailed architecture for this design. Following is a detailed architecture for this problem. It involves various components like application servers, databases for storing try, caches for fast retrieval, load balancers, and the ranking service. Typeahead suggestions is a very complex problem, and thus we will discuss this design in great detail in one of our future videos. So, subscribe to our channel to get notified. For now, let us move to the next question. Another popular system design question is to design top-end songs. This question has become more frequent in recent times. This question is very similar to designing the system for top-end trending topics. Here, we will be asked to develop the back-end of the service, to get the top-end songs for a user over the past X days. For simplicity, let us assume that the popularity of a song can be determined by the frequency of the song being listened to in the past. Next, let us discuss the design goals and scale estimations for this problem. While designing this system, we should ensure that the system has minimum latency. So, the user does not experience any significant lag during the queries. The final design should be highly available. As we know from the CAP theorem, we can have either high availability or high consistency. Thus, we will aim for an eventually consistent system. Our system will also be write-heavy in nature, as more users will be listening to songs, rather than fetching the top-end songs that they have heard so far. Thus, the number of write requests will be far greater than read requests. For an efficient system, we will have to consider the following scale estimations. On average, the system will have 250 million monthly active users, about 1 billion songs will be listened to each day, and about 200 million daily read requests will be made to get the top-end songs. Now, let us discuss the REST APIs required for this question. To interact with the system, we will need two REST APIs. The first one is the Get Top Songs API. It is a read API to fetch the top-end songs over the past X days. The client will send user ID, maximum number of songs to be returned, duration, and timestamp as the request parameters. The second one is the Record Song API. It is a write API to record when the user listens to a song. This API requires user ID, song ID, and timestamp as the request parameters. Now, let us discuss a high-level design for this problem. At a high level, whenever the user listens to a song, we will log it on the application server. A background asynchronous process will read the data from these logs, do some initial aggregation, and send the data for further processing. The aggregated data will be sent to a distributed messaging system like Apache Kafka. Then, we can divide our system into two paths, fast path or slow path. In the fast path, a data structure called count-min-sketch will be used. It will calculate the top-end songs approximately, and the results will be available within seconds. In the slow path, a MapReduce pipeline will be run to calculate the top-end songs precisely. This may take minutes or hours for the results to be made available. In the interview, discuss the pros and cons of both the paths with the interviewer, and then choose either path depending upon the system constraints, that whether we need near real-time results or if some delay is acceptable to achieve accuracy. Following is a high-level architecture diagram of this problem. We have also added a link to a YouTube video from another channel in the description box below. We suggest going through it to better understand the concepts related to this question. As this is a challenging problem, and to not make this video very long, we will be creating a dedicated video to discuss this question in great detail. So, subscribe to our channel to get notified. For now, let us move to the next question. User privacy has been a critical topic currently for most tech companies. On Facebook, you may have noticed that you can set different privacy levels for the posts you publish, to be only visible to a specific set of users like public, friends, friends of friends, etc. The privacy implementation design can be fairly complex, so we will limit it to a few core features that can be covered in a 45-minute interview round. We will be asked to develop the back end of a system that will enable a user to specify the different levels of privacy for a post, so that it is only visible to a particular set of users on Facebook. To keep the discussion simple, we will only implement 2 levels of privacy, public and friends, for this question. More complex levels like friends of friends and custom groups can be discussed towards the end of the interview if the time remains. Now, let us discuss the design goals and scale estimations for this problem. We should ensure that our design has minimum latency, and users should not experience any lag on Facebook. The system should be highly consistent, as the same privacy settings should be applied across all devices. As per the CAP theorem, we can ensure either high consistency or high availability, but not both. Thus, we will tolerate lower availability in the interest of high consistency. Our system will also be read-heavy in nature. We will need to make a large number of read requests to check the privacy level of existing and new posts, to make them visible to the correct users. But, a much fewer number of write requests will be made to set the privacy level of the new posts. Thus, the number of read requests will be far greater than write requests. For an efficient system, we will have to consider these scale estimations. The system will have 1 billion daily active users. The privacy level will be set by the users for about 2 billion posts daily, and we will need to check the privacy level of about 100 billion posts daily, so that they can be made visible to the correct users. Now, let us discuss the REST APIs that we will be developing for this problem. To interact with the system, we will need 2 REST APIs. The first one is the Set Privacy Level API. It is a write API to set the privacy level for a particular post. The client will send user ID, post ID, privacy level enum, and timestamp as the request parameters. The second one is the Can View API. It is a read API to check if a user can view a particular post or not. This API requires viewer ID, post ID, and timestamp as the request parameters. Next, let us discuss the high-level design for this question. To define the different privacy levels, we will use the enum data type. The elements of this enum will be public, friends, friends of friends, and custom. This enum will be stored along with each post in the database. To check whether a particular post is visible to a specific user or not, we will review the privacy level enum. If it is set to public, then it will be visible to everyone. If it is set to friends, we will check if the current user is a friend of the post's owner. If yes, then the post will be displayed on the UI. We will also need to discuss how we will store and fetch the user's friend list to efficiently check if the post can be displayed. One possible way is to store this data in a key value store. Here, the key will be the user ID, and the value will be a set of all the friends that the user has. Since the friends data at Facebook will be massive, it will not fit on a single machine. We will have to shard this data across multiple servers. This data can be sharded using the user ID as the key. We will also need to discuss what will happen if a shard dies, and create a fault-tolerant design. Implementation for friends of friends is an excellent follow-up for this question. Given the scale of Facebook, we cannot enumerate through all the friends of friends, as it will be an extensive list and increase the system's latency. One possible way to solve this challenging problem is to perform an intersection of the post's owner and the viewer's friend lists. If the intersection results in a non-empty set, the viewer is a friend of the owner, and thus the post can be displayed. Following is a detailed component design of this problem. It shows the two REST APIs and their interactions with the application servers, load balancers, databases, and caches for fast retrieval. Same as before, we will be making a separate future video for this design to discuss it in more detail. So, do subscribe to our channel to get notified. For now, let us move to the next question. Like many search engines, Google uses a software program named Web Crawler to scan the World Wide Web. It downloads and indexes all the web pages, to be made available for the search queries submitted by the users. In this question, we will be asked to design the backend of a web crawler. Given a list of seed web pages, it should download all the web pages, and index them for future retrieval. Also, the service should handle duplicate web pages so that unique URLs are stored. Now, let us review the design goals and scale estimations for this problem. We should ensure that our service is highly scalable, as it needs to crawl the entire web and fetch billions of web pages. It should implement the robot exclusion protocol, which allows the webmasters to declare parts of their websites off limits to crawlers. For the simplicity of the interview, we can consider that we will crawl only HTML pages. To design an efficient system in the interview, we will have to consider the following scale estimations. Our system will be crawling about 25 billion web pages every 2 weeks. On average, each URL will be 512 bytes in size, and each page will be about 100 KB in size. Now, let us discuss the high-level design of the web crawler. Web crawler will take a list of seed URLs as its input, and recursively perform the following steps. 1. It will pick a URL from the list of unvisited URLs. 2. It will determine the IP address of its hostname. 3rd, a connection will be established to the host to download the corresponding document. 4. The document contents will be parsed to look for the new URLs. 5. These new URLs will be added to the list of unvisited URLs. 6. The downloaded document will be processed, and then its content will be stored and indexed. And 7. Repeat the same process from step 1. For the traversal method, we will use breadth-first search to crawl the web pages. However, depth-first search can also be utilized in some situations. If we have already established a connection with the website, we can use DFS to crawl all the URLs within this website to save some handshaking overhead. Now, let us take a look at the main design components of a web crawler. A bare minimum crawler will need at least the following design components. 1. URL frontier will be used to store the list of URLs to download, and prioritize which URLs should be crawled first. 2. HTML fetcher will retrieve a web page from the server. 3. Extractor will extract the links from HTML documents. 4. Duplicate eliminator will make sure that the same content is not extracted twice unintentionally. And 5. Data store will be used to store retrieved pages, URLs, and other metadata. Next, let us review the detailed component design of this problem. Following is the detailed component design of the web crawler. It involves various components like URL frontier, HTML fetcher, extractor, duplicate eliminator, and data store. You can support us by buying us a coffee by clicking the link in the description box below. Kindly join our Patreon community to support us, and take advantage of our additional services like detailed resume review, early access, and shout out in our videos. This video is the second part of the 2-part video series on system design interviews at Facebook. Thus, if you haven't watched the first part, we recommend watching it by clicking the above link in the top right corner of this video, or through the link that we have added in the description box below. We recommend you to take a look at our kit.co page in the description box below, for interview preparation books and courses. It also contains additional details about our work-from-home setup, and the tools used to produce this video. We hope that this video and the resources mentioned in the description will help you in your journey in preparing and succeeding in these interviews. We'd like to thank you for supporting our channel by giving us a like, leaving a comment, and sharing this video with your friends. Also, subscribe to our channel, and press the bell icon to get notified when we publish detailed solutions to each of these problems in our future videos. See you all in the next video.